Salutations. We are interested in the task of poverty prediction through satellite imagery.
To give a brief overview of our problem, we aim to use daytime imagery and a generative framework in order to learn class label distributions. So the reason we use daytime imagery instead of nighttime imagery, which is currently used in most state-of-the-art models, is because nighttime imagery is a little more difficult to acquire in high resolution. So our dataset consists of 40,000 cities from around the world. We normalize wealth indexes from -2 to 2. As you can see, our distribution of wealth is bimodal. However, we use a 3-class prediction because that's what's currently used in literature. Our discriminative baseline consisted of convolutional layers followed by fully counted layers. We also used a generative baseline, which was the pix-to-pix image-to-image translation model, which we use to generate nighttime images from daytime images.
We also explored a conditional multi-class scan where we not only predict real or fake, but which of the K classes a given daytime image was in.
Next, we moved on to a slightly more complicated model. We know it as a 3-step transitional model, which the heart of the model was again conditioned on the daytime image. From the daytime image, it generated the nighttime embedding of that image, and then uses that nighttime embedding to predict the poverty level.
So the 3-step translation model produced the best overall accuracy. As you can see from the confusion matrix, also, as we expected, most of the errors come from predicting consecutive classes. We have very few errors that mistake poor for wealthy or wealthy for poor.
A little bit more error analysis here. We decided to delve deeper into our data set and see the percentage of each of our classes to see what kind of terrain they included. One important note to see is richer areas contained more ocean than poor areas. This correlated strongly with our model and where it made errors. As we can see here, we analyzed where our model incorrectly labeled poor images as rich and rich images as poor.
We also investigated the actual embeddings that were generated and plotted them using t-SNE. So we looked at the actual networks that were generating the embeddings and discovered that it was best to do so using a VGG network. We looked at the dimensionality and found that the kind of magic number for the dimensionality was 1024, somewhere in the middle. And we also saw that as we trained our network in a 2-class setting, going from 2-class to 3-class to regression, our model still learned meaningful translations between those different settings.
So in conclusion, our final model got a 71.6 test accuracy, which is a significant improvement from our baselines. And more importantly, this demonstrates potential for the use of daytime imagery to predict poverty using generative approaches, which has huge promise over the current state of art, which only uses nighttime imagery. If you wish to learn more about our final report, please read our final report.